In this video, we'll take a look at linear approximations. Now, suppose we have a function f of x, and it looks like this. So this will be our f of x, and we are considering the tangent line at x equal to a. Suppose that a is down here, and we're looking for the tangent line at this point. Now this tangent line will have a point at a comma f of a and a slope of the derivative of our function f at a. Using our point slope formula, we'll have that an equation for this line is y minus f of a equal to the slope f prime of a times x minus a. If we solve for y in this equation, we'll have y equal to f prime at a, x minus a, plus f of a. Now, this is the equation for our tangent line, but if we're close to a, this tangent line would be a good approximation to our function f of x. This equation is called the linearization of f of x at a, and often it replaces that y with capital L of x. So again, this is what's referred to as the linearization of f of x at a. So let's look at an example where we're asked to find the linearization of a function at a specific value of a. Let f of x equal to the square root of x plus 3. And here we're asked to find the linearization of f of x at a equal to 1. All right, so to find the linearization, we need some ingredients. We need a point, and we need a slope. For your point, you're looking at what you get for our function when we plug in 1, and f of 1 is simply going to be the square root of 4, or 2. For our slope, first we need to find the derivative of our function f of x. So f prime of x in this case would be 1 over 2 square root of x plus 3. And then we're going to take this function and evaluate it at 1. So that's 1 over 2 square root of 1 plus 3. So that's 1/4. So again, we needed our point and we needed our slope that we get to use to evaluate our linearization. So our linearization function, capital L of x, is equal to f prime of a times x minus a plus f of a. And in this case, our a is equal to 1. F prime of 1 is 1/4, and f of 1 is 2. So this would be the equation for our linearization. So again, the aim is to be able to approximate our function, square root of x plus 3, with this linear function, 1/4 x minus 1 plus 2. We can open up a graphical utility and graph both of these to convince ourselves that our line is a good approximation to the square root of x plus 3. So here on Desmos, I have my function f of x, square root of x plus 3, graphed out in black. And our tangent line, 1/4 x minus 1 plus 2, in red. I'm going to evaluate both functions at values close to 1, and their values are going to be listed right here. The black corresponds to the values of my function f of x, the square root of x plus 3. The red corresponds to the values of my line, 1/4 x minus 1. And as I take the slider and move it away, I'm evaluating it at different values of x close to 1. So when I'm plugging in values close to 1, let's say here at 1.15, here are my two values for my two functions. My square root function is about 2.037. My line is 2.037, right? They're pretty close to each other. So you can approximate your functions really well when you have values of x that are close to 1. Now, if we push it a little bit forward, let's say where my x value is 3.85, the value of my square root function is about 2.617, and my value for the line is 2.712, 2.713, right? So you start seeing some discrepancies between the two values, my two functions, right? In some cases, this might be good enough. It might be practical to use these values, but as a general rule, you want to always select values close to your a. So in this case, my a was 1. So in this case, I should select values that are close to 1.